This is the sixth concrete session. We will talk today about the design of two-way slabs. Today, it will be specifically designed for flexure and tomorrow designed for shear. I had told you last week that we will cover the portions of the development length session that could not be covered because of a lack of time the other day. These were the two examples and the question and answer. I am going to postpone that until tomorrow because tomorrow's slide set is long. I don't think it will leave us time. Tomorrow's is shorter and I can make the lecture a bit shorter than the slide set is. And tomorrow we will spend time on the two leftover development length examples and we'll answer your questions on both development length and tomorrow's lecture. Okay, first of all, the scope that we are covering today when we say the design of two-way slabs, and whatever is written on this page, I have in figure on the next page. So let us look at this pretty carefully. What is our scope when we say design of two-way slabs? Slabs originally used to be supported on beams on all four sides, as you see in the first picture. Now, this type of a slab transfers loads by bending in both directions, in the short direction and in the long direction. The short direction is stiffer, so bending in the short direction transfers more load than bending in the long direction. Now, if the long side to short side ratio of the slab panel is 2 or more, then bending in the long direction becomes unimportant. It does not transmit much of the load on the slab to the beams. So at that stage, we consider it to be a one-way slab, bending only in the short direction. So this beam-supported slab can be a one-way slab when the long dimension to short dimension ratio of the slab panel is 2 or more. And as the ratio approaches 1, then bending in both directions are equally important. And so below 2, we consider it to be a two-way slab. In other words, the loading on the slab is resisted by bending of the slab in both directions. Now, as time progressed and technology evolved, those column line beams began to disappear. I would say already in the 1920s and 30s, about 100 years ago, for reasons of formwork simplicity. Those beams along the column lines take a lot of money to form. And remember our discussion the other day, formwork accounts for about half the cost of a concrete structure. So we really cannot afford expensive formwork. Okay. When there are no column line beams, we have a slab supported directly on columns, and that is called the flat plate. Currently, the most popular, definitely concrete slab system I would say it is one of the most popular in any material. The big attraction of this slab system is that you get the shallowest, uh, what we call the ceiling sandwich. The you don't need any false ceiling or anything. So with the flat plate, the story height can be the smallest. Uh, like among all the slab systems available to us, the flat plate slab system will give us the shallowest story height, which you translate into a lot of savings in, first of all, cladding, secondly, electrical cables, HVAC ducts, telephone cables, anything that goes up a building. So that makes the flat plate, as I said, the most popular slab system there is in concrete for sure. Now, the problem with the flat plate is two-way shear or punching shear around the columns. As the span gets larger or the loading on the slab becomes higher, we develop problems with punching shear around the columns. So fairly often, the slab is thickened locally around the columns, creating what are called drop panels. And when a slab, a flat plate, is equipped with drop panels, we don't call it a flat plate anymore. Then it is called a flat slab. Okay. Now it is kind of strange that a flat slab is not flat. Okay, a flat plate is flat, but a flat slab has these local thickenings, making it not flat. But that's nomenclature that we have used for a long time. For the same reason of punching shear, the column top is quite often flared, creating what are called column capitals. Now, the column capital is part of the column. It is not part of the slab. So that does not change the nomenclature of the slab. Whether we have a column capital or not does not make any difference. If there are those drop panels, we have a flat slab. Without those drop panels, a column supported slab is a flat plate. The final slab system shown is the same as a flat plate, except we have removed some of the tension concrete, which does not do anything for us anyway, to save on the weight. Now, obviously, we do not cast a solid slab and then remove the tension concrete. There are ready-made formworks available for rent around the country that will produce that structure for us. This is called a waffle slab because it looks like the waffles that we eat. Notice that the slab around the column is not ripped, it is solid. And that again is because of punching shear. So we have two-way beam supported slabs where the ratio of the long side to the short side of the slab panel is less than 2. We have flat plates, we have flat slabs, and we have two-way ribbed slabs, which are called waffle slabs. All of that is covered in today's discussion. Now, one of the very first and fundamental things we absolutely have to understand about flat plates is what I'm trying to explain with the help of this particular picture. Now, let us take a beam supported slab. Let us say the slab strips spanning in the short direction transfer 60% of the slab load, and the slab strips spanning in the long direction transfer the remaining 40% of the slab loads. Now, the 40% of the slab loads that are transferred by bending in the long direction, those loads are transferred to beams B1, which span in the short direction. Okay, so 60% of the load on the slab is transferred by bending of the slab strips spanning in the short direction, and the remaining 40% of the load on the slab is transferred by the beams bending in the short direction to the supporting beams. So the slab strips running in the short direction plus the beams running in the short direction transfer 100% of the slab loads. Similarly, the beams spanning in the long direction and the slab strips spanning in the wrong direction together also transfer 100% of the slab loads. Now, when there are no column line beams, we have a flat plate, a slab supported directly on columns. We can imagine beams concealed within the thickness of the slab. You will see that in the design of flat plates or two-way slabs, we divide the slab we divide a slab panel into a middle strip and then a half column strip on either column line. So half column strip from the right panel, half a column strip from the right panel, and half a column strip from the left panel will give us a full column strip along the column line. So we have middle strip and column strips. Okay, those column strips are nothing but beams of the same thickness as the slab that are concealed. Okay, now if you imagine strips of slab running in the left to right direction, let us say they transfer 40% of the slab load. Okay, and those column strips transfer the other 40%. So the point is that just like in this picture, the slab strips running in the short direction and the beams running in the short direction transfer 100% of the slab load. Similarly here, the slab strips running in the up and down direction and the column strips running in the up and down direction together transfer 100% of the slab loads. In the left to right direction, the same thing. The middle strip running in the left to right direction plus the column strips running in the left to right direction transfer 100% of the slab load. So a flat plate has to transfer 100% of the slab load by bending in each orthogonal direction. This is something fundamental that was not understood at the beginning of the flat plate back in the 20s and 30s. By the 40s, I think most engineers understood this, but before that, there were problems because of a lack of understanding of this fundamental, that a flat plate transfers 100% of the slab load by bending in each orthogonal direction. Now, provisions of ACI Chapter 13 and BNBC Section 6.5 shall apply for design of slab systems reinforced for flexure in more than one direction with or without beams between supports. This slide is talking about irregularly shaped supports, and I will let you read it. That's not a very usual situation. Solid slabs and slabs with recesses or pockets made by permanent or removable fillers between ribs or joists in two directions are included in the scope. So those pockets and fillers are not uncommon, and that does not remove the slabs from the scope of Chapter 13. Minimum thickness of slabs are given actually in Chapter 9, and we have discussed some of it, and we will rediscuss some of it. For slabs supported on walls rather than beams, the explicit design procedures in this chapter treat the wall as a beam of infinite stiffness. That's what a wall is, a very, very high stiffness. Therefore, each wall should support the entire length of an edge of the panel. Okay, so if it is wall supported, wall should support the entire edge. Wall-like columns, long columns, less than a full panel length, can be treated as columns. So if the full panel length is not supported, then a wall-like column is treated as a column, not a wall. Okay, this talks about minimum thickness and which section or table you go to. So let us, okay. For slabs without interior beam spanning between the supports, having a ratio of long to short span not greater than 2, the minimum thickness shall be in accordance with table 9.5c. We will take a look at the table. We have seen it before. But there are absolute minimum thicknesses. Slabs without drop panels, 125 millimeters is the absolute minimum thickness. So flat plate cannot be more than 5 inches thick. Slabs with drop panels, the slab itself outside of the drop, cannot be any less in thickness than 100 millimeters, 4 inches. Now, table 9.5c, which gives you minimum thicknesses of slabs, is this table. So there are values for slabs without drop panels and values for slabs with drop panels. Exterior panels, interior panels, different minimum thicknesses, although in reality, we typically will not provide minimum thicknesses for different panels. Anyway, this is the yield strength of the reinforcement for 420 MPa reinforcement. So a flat plate does not have column line beams, but you can have edge beams, okay, perpendicular to the column line. So that is permitted. It used to be more common than it is today, but anyway. So without edge beam, this is the pure flat plate, no beams of any kind. L sub n over 30 is the clear span divided by 30 is the minimum thickness. And when we say clear span, it is the length of clear span in the long direction. If the two directions are different in span, then it is the span in the long direction. For slabs with beam spanning between the supports on all sides, minimum thickness shall be as follows. So flat plate is given by the table 9.5c. If you have beams on all 4 sides, then for alpha sub fm, this is the stiffness of the supporting beams. You will see exactly what that quantity is, equal to or less than 0.2. Those will be treated like flat plates. If the beams supporting the slab panel on 4 sides are not very stiff, as indicated by alpha sub m equal to or less than 0.2, then it will be treated as a flat plate, as if the beams were not there for the purposes of minimum thickness. If the average stiffness of the beams around the perimeter is between 0.2 and 2, then minimum thickness will be given by this expression, and the thickness shall not be any less than 125 millimeters. Okay, alpha sub fm you have seen. The beta is it is explained later. I think it is the long side to short side ratio of the panel. You will see someplace. I don't see it offhand, the explanation for beta. Okay, so then if the beams are very stiff, alpha sub m fm greater than 2, then the expression changes to what you see. Sorry. Then the expression changes to what you see in the picture. Now the minimum is 90 millimeters. Now at alpha sub m, I haven't explained yet, but the idea is if the supporting beams are not stiff at all, then it is a flat plate. If the supporting beams are very stiff, then the minimum thickness is given by this expression. If the supporting beams are kind of moderately stiff, then minimum thickness is given by the expression on the previous slide. At discontinuous edges, an edge beam shall be provided with a stiffness ratio not less than 0.8, or the minimum thickness required by equation such and such shall be increased by at least 10% in the panel with a discontinuous edge. This is a pretty serious requirement. Okay, so when we have this panel supported by beams of moderate stiffness at discontinuous edges, edge beam shall be provided. Discontinuous edges of the slab beam shall be provided with a stiffness ratio not less than 0.8, or minimum thickness required by that equation shall be increased 10%. Beta is explained here. Term beta in B and C is ratio of clear spans in long to short direction of slab. I said long to short dimension ratio, whatever, this is more exact. Beta is the ratio of clear span in long to short direction of slab. Yeah. Alpha sub f, very importantly, is ratio of flexural stiffness of beam section to flexural stiffness of a width of slab bounded laterally by central lines of adjacent panels on each side of the beam. So alpha sub f, I will read it again and then I have a picture. Ratio of flexural stiffness of beam section to flexural stiffness of a width of slab bounded laterally by center lines of adjacent panels. So this is center to center line of panel to center line of panel slab width stiffness of that. Alpha sub fm, so there is a beam on each of the four sides. Alpha sub fm is the average value of alpha f for all beams on edges of a panel. Yeah. Now, so it is beam to slab stiffness ratio, the slab from center line of this panel to center line of this panel. Okay, the slab part is clear. What is the beam? There is a beam sticking below the slab, but a portion of the slab is also treated as part of the beam. And that portion is so this is equal to whatever is sticking below the slab. And that is A minus H. So this overhanging width is equal to whatever part of the beam is sticking below the slab, except this cannot be taken any wider than 4 times the thickness of the slab. Okay. So if you look at the two pictures, you will see it's quite clear. So the beam is the shaded portion, including a part of the slab, and alpha sub F is the beam stiffness divided by the slab stiffness, slab being panel to panel width of the slab. That's alpha sub F. Now, slab thickness less than the minimum required shall be permitted where computed deflections do not exceed the limits in table 9.5b. This we saw for beams and things. Deflection shall be computed taking into account size and shape of the panel, conditions of support, nature of restraints at the panel edges, modulus of elasticity shall be specified in, etc., etc. Okay? Now, so you can provide the minimum thickness as in the case of beams, or you can calculate deflections and show that the calculated deflections are within tolerable limits. There are short-term deflections and long-term deflections, as in the case of beams. The same long-term deflection multiplier applies. But to calculate the deflection of a two-way slab is infinitely more complicated than calculating the deflection of a beam. I'm not going to say it cannot be done, but it is difficult to do. So this is not an option that you should normally choose. And if you have an interest in how to calculate the deflection of a two-way slab, you will have to go to good standard textbook. Even then, you will only have a how should I say it? Only an idea. You have to do it a few times to get a feel for this. Anyway, you will need EI in deflection calculation. E is the E sub C as given in ACI 318 or BNBC 2020. The effective moment of inertia is given by this expression. This we went over when we discussed beam deflection, nothing different. This table also we have seen, we have two sets of limitations, two sets of limits. One applies to immediate deflection upon application of dead load, upon application of live load. So as soon as you apply live load on your slab, there is immediate deflection. Those are limited to either L over 180 or L over 360, depending upon this and that. So flat roofs not supporting or attached to non-structural elements likely to be damaged by large deflections L over 180. Floors not supporting or attached to non-structural elements likely to be damaged by, then it is L over 360. So if damage to non-structural elements is unlikely, L over 360. If it is likely, then tighter limit of L over 180. Or did I say? I probably said it backwards. So when damage to non-structural elements is not likely, then the deflection limit is more liberal. If damage to non-structural elements is likely, then the limit is tighter. The second set of limits applies to that part of the total deflection occurring after attachment of non-structural elements. So that would be sum of the long-term deflection due to all sustained loads and the immediate deflection due to any additional live load. Okay, all of that we went over in discussing beams, Anyway, I would suggest that you do not get involved in uh, calculating deflections of two-way slabs and trying to show that they're within limits. You are much better off not making them particularly in big, because that will bring you problems down the road. Now, when we design slabs, uh, what we do is what is being suggested on this figure. First of all, when we talk about slab panel, it is a portion of slab as shown in the picture between beams or walls or edges, whatever, you get the picture. And then we design the slabs by cutting uh, by cutting those portions out of our structure separately into orthogonal directions. So we cut this portion out of the structure, take it out for design of the beams, for design of the slabs that you see uh, shaded, and then we take this, we cut this portion out of the building for design of the slab strip running in the left to right direction. Okay, so this strip is taken from panel center line to panel center line, and that strip also is taken from panel center line to panel center line. Here I was trying to show that if the column layout is not exactly symmetrical and everything, then instead of a straight line, you may end up with a line like that. Your panel center line may look like that if the column layout is irregular. Now, when you take a chunk like that out of your building, this is what you end up with: a set of columns supporting the strips of slab, and the strips of slab run between panel center lines. Okay. Now, when we are considering lateral loads due to wind or earthquakes, this is our subsystem below which we cannot go. We have to analyze this thing, and we do. But when we are treating gravity loads, when we are considering our slab subject to gravity only, then we can reduce this subsystem further down to what you see at the bottom. We can take a slab strip on any particular level as shown in the picture, and then we can take the columns that are directly supporting the slab strip. The columns above the slab strip will be considered fixed at the upper level, and then the columns below the slab strip will also be considered fixed at one level below. So this is our slab strip at a particular level. These are the attached columns. The columns below will be considered fixed at the level below, and the columns above will be considered fixed at the level above. This subsystem will give you sufficiently accurate predictions of bending moment, shear forces, etc. Under gravity loads. Okay, so under lateral loads, this is our subsystem. Under lateral load, this is our subsystem. This is the direction of analysis. So we now talked about design strip from panel center line to panel center line. Okay, keep that language, that terminology in mind. Design strip, I will use it quite a bit. The design strip as I was trying to indicate earlier, is divided between column strip and middle strip. Column strip is a design strip with a width. I think a picture will be better. Okay. So column strip and middle strip. So from here to there is a design strip from panel central line to edge of the panel. And then panel central line to panel central line is another design strip. And then there is another design strip and so forth. L sub 1 always by definition is the span in the direction of analysis. Sub 1 indicates that. And L sub 2 is the transverse span, orthogonal to the direction of analysis. If L sub 2 is smaller than L sub 1, as in the left picture, then the width of the half column strip is L sub 2 over 4. The width of this half column strip is also L sub 2 over 4. Now, here, the two spans are equal. This is L sub 2, that is L sub 2. So this is also L sub 2 over 4 for a column strip width of L sub 2 over 2. Okay? And whatever is left over is the middle strip. Here, the half column strip is L sub 2 over 4. The half column strip here is L sub 2 over 4. So the remaining L sub 2 over 2 is the middle strip. I think you get the idea. Now, if this span were different from that span, if this were L sub 2A and this were L sub 2B, this would be L sub 2A over 4 and this would be L sub 2B over 4. Okay. Now, in the second picture, L sub 2 is smaller than L sub 1. I'm sorry, L sub 1 is smaller than L sub 2. So now the width of this half column strip is L sub 1 by 4, the shorter span divided by 4. This is L sub 1 by 4. This is L sub 1 by 4. So the width of the half column strip is 1/4 of the shorter span, L sub 1 and L sub 2. Okay, I think the picture is explicit enough. So that defines the column strip and the middle strip. A panel is bounded by column, beam, or wall central lines on all sides, as you have seen. For monolithic or fully composite construction, a beam includes that portion of a slab. Let me go to the picture. So when we talk about a beam, it is the physical beam, but also a portion of the slab. How much of the slab? Whatever part of the beam is sticking below. So H sub B, width of the slab, is taken as part of the beam, but H sub B shall not be taken any more than 4 times the thickness of the slab. This we saw before when we were discussing the beam to slab stiffness ratio. Okay. When there are slabs on both sides of the beam, it is no different. Okay. So this overhang is equal to H sub B as shown here, but cannot be any more than 4 times H sub F. So the beam includes a portion of the slab as defined in this figure. Now, the slab thickenings that I discussed with you, when used to reduce the amount of negative moment reinforcement over a column or minimum required slab thickness, a drop panel. So the local thickening of the slab, I said, is mainly for reasons of punching shear, but it is also utilized to reduce the amount of negative moment reinforcement over the column or to reduce the minimum required slab thickness outside of the drop panel. If that's what we are trying to do, then the drop panel has minimum dimensions. It must project below the slab at least 1/4 of the adjacent slab thickness. So if the slab is 8 inches thick, the drop panel cannot be any less than 2 inches. Okay. And the drop panel must extend in each direction from the central line of the support a distance not less than 1/6 the span length measured from center to center of supports in that direction. The details aside, the point is that the thickness of the drop panel, minimum thickness is given, and the drop panel must extend into the spans for a certain distance. Otherwise, they're technically not drop panels. Yeah. So this is much more clearly understandable. A drop panel minimum thickness is 1/4 of the slab thickness, and it must extend 1/6 of the span length into each span. So this is a requirement of a drop panel. When used to increase the critical concrete section for shear at a slab column joint, okay? So if we are not trying to decrease the reinforcement of the bending moment, our purpose is only to increase shear capacity, then the projection is called a shear cap, not a drop panel anymore. And a shear cap also has dimensional limitations. If it sticks below the slab by a distance A, then this horizontal distance will also be at least equal to A. Okay. So we have drop panels that have minimum dimensional requirements, and then we have shear caps, which also have these minimum dimensional limitations as shown very clearly in the picture. Okay. Now we go to slab reinforcement. Area of reinforcement in each direction for two-way slab system shall be determined from moments at critical sections shall not be less than required by shrinkage and temperature reinforcement. Obviously, reinforcement will be dictated by bending moment, but the flexural reinforcements shall not be any less than the shrinkage reinforcement. This is very, very important. Okay. The flexural reinforcement that must be placed near the tension phase shall not be any less than shrinkage reinforcement, which is typically 0.18% of gross, except that if you have high strength reinforcement, you can go below 0.18% of gross, but cannot go below 0.14% of gross. So shrinkage reinforcement given in section 712 of ACI 318 and section such and such of BNBC 2020. So flexural reinforcement shall be dictated by how much bending moment we have to resist, but it shall never be any less than the shrinkage reinforcement. Spacing of reinforcement at critical sections shall not exceed 2 times the slab thickness, except for the exception I'll let you read is not terribly important. So 2 times the slab thickness is the spacing of reinforcement. The maximum spacing is 2 times the slab thickness. Okay. Now anchorage, very important, and I will read and maybe not try to do much more than that because time is running and this is a pretty long thing. So but this is all important stuff. Positive moment reinforcement perpendicular to a discontinuous edge, this is the bottom reinforcement, shall extend to the edge of slab and have embedment straight or hooked at least 150 millimeters in spandrel beams, columns, or walls. So this is anchorage or positive reinforcement at the discontinuous edge. Negative moment reinforcement perpendicular to a discontinuous edge shall be bent, hooked, or otherwise anchored in spandrel beams, columns, or walls, and shall be developed at face of support according to section such and such. Okay. This is anchorage. Again, I just said that I will read it. I think it is understandable upon reading. If not, you have to think about it or find pictures to look at. Where a slab is not supported by a spandrel beam or wall at a discontinuous edge, how then are you going to, it is not supported by a beam or wall. So how do you anchor the reinforcement? Or where a slab cantilevers beyond the support. Now, anchorage of the reinforcement shall be permitted within the slab. Okay, so you will hook it inside the slab or go for headed bars or mechanical anchorage, whatever. So you have to anchor it within the slab. Then there is something called corner reinforcement. I don't want to spend a lot of time on this because this is only for beam supported slabs. And I think the emphasis more and more is on flat plates. So let me show you maybe the details are here and you can read for yourself. I there is a little bit of commentary that I wanted to read. Just 1 second here. So unrestrained corners of two-way slabs tend to lift when loaded. I think this is, you can visualize this, right? Beam supported slab, unrestrained corners tend to lift when loaded. You have the slab supported on beams, you are loading the slab, so the corners want to lift off. If this lifting tendency is restrained by edge walls or beams, bending moments result in the slab. So the slab wants to lift off. You are not letting it lift off. That will set off bending moments in the beams. This section of the code provides steel to resist these moments and control cracking. Reinforcement provided for flexure, etc. Those are details that I'll let you read up. Now, the provisions say that you shall provide the reinforcement in the, I think that may be worth reading. 1 second. Yeah. Corner reinforcement shall be placed parallel to the diagonal in the top of the slab and perpendicular to the diagonal in the bottom of the slab. Okay. So top reinforcement will be parallel to the diagonal at the top of the slab and perpendicular to the diagonal at the bottom of the slab. Alternatively, reinforcement shall be placed in two layers parallel to the sides of the slab in both the top and the bottom of the slab. This is what we almost always do, not the diagonal, which is very difficult to place. Two layers of reinforcement as shown in this picture. Okay. So corner reinforcement only for beam supported slabs where the beams are reasonably stiff. This is something you have to be aware of, but I think that's probably enough time spent. When a drop panel is used to reduce the amount of negative moment reinforcement over the column of a slab, the dimensions of the drop panel shall be, we went over that. In computing required slab reinforcement, the thickness of the drop panel below the slab shall not be assumed to be. So what this is you saw that the minimum thickness of the drop is 1/4 of the slab thickness. So what sticks out below the slab cannot be any less than 1/4 the thickness of the slab. If you have more than 1/4, then this is saying that you will ignore the remainder. So the thickness of the drop panel below the slab shall not be assumed to be greater than 1/4 the distance from the edge of the drop panel to the face of column or column capital. it is not exactly what I said. It is not saying disregard anything that is more than 1/4 the thickness of the slab. It is saying, so let us read: the thickness of the drop panel below the slab shall not be assumed to be greater than 1/4 the distance from the edge of drop panel to the face of column or column capital. Okay, so this is the, you will not take it any more than 1/4 of the thickness of the slab plus the drop. That's what it is saying. Anyway, you will understand it if you read it closely. Now this is very next thing is very important. Uh, the I'll come back. So this is the only, seriously, the only figure in all of ACI 318. There are many figures in the commentary, but none, not a second one in the code. And this tells you about the extension of the slab bars. These are the column strip bars above the double line. These are the middle strip bars below the double line. These are the top bars in the column strip. These are the bottom bars at the column strip. The top bars must extend so much into the span. These top bars must extend so much into the span. Okay, so this picture is an absolute necessity to understand and to comply with. So please take a look. I will not be able to improve anything by dwelling on every number here, but I do want you to understand that this very important picture is part of the code and you are supposed to follow it. Okay, so so reinforcement in slab shall have minimum extensions as prescribed in that figure. Where adjacent spans are unequal, extensions of negative moment reinforcement beyond the face of support shall be based on requirements of the longer span. So that I think makes a lot of sense. So this is 33% of L sub n, this is 30% of L sub n. If this span and that span are different, then you will, this L sub n, the clear span shall be the clear span, the longer clear span. Okay, so both directions you will extend by this way it will be 30% of the longer span. This way it will be 33% of the longer span. Not if the left span is shorter than the longer span, this will not be 30% of the shorter clear span. So yeah, so this you should read, and then the rest of it are details that I think I okay. Uh, this is, I think, rather different from everything else that we are discussing in connection with slab reinforcement. This is what we call structural integrity reinforcement. The idea is if something happens to, if there is extraordinary loading or a column gets knocked out or something, the slab should keep on hanging in place. It is not expected that everything will be the same as before the column got knocked out, but our expectation is that the slab should not end up on the ground or on the floor below. It should be hanging in place. And that requires structural integrity reinforcement. This is extremely important. And this is what the code requires. All bottom bars within the column strip in each direction, all bottom bars, shall be continuous or spliced with class B tension splices or with mechanical or welded splices satisfying section such and such. Splices shall be located as shown in figure. So the figure shows where you can put the splices. At least two of the column strip bottom bars in each direction shall pass within the region bounded by the longitudinal reinforcement of the column and shall be anchored at exterior supports. So all column strip bottom bars must be continuous, with two of them passing through the column cage. That's the summary of it. This is structural integrity reinforcement that I cannot tell you how beneficial this requirement has been and how many buildings it has saved after explosions and things like that. Highly, highly important. All column strip bottom bars shall be continuous with two of them passing through the column cage. Openings in slab. Openings of any size shall be permitted if shown by analysis that the design strength is at least equal to required strength and that serviceability conditions are met. Now, as an alternative to that kind of analysis, these are simple rules that you can follow. Openings of any size shall be permitted openings of any size shall be permitted in the area common to intersecting middle strips, provided total amount of reinforcement required for the panel without the openings is maintained. Yeah, whenever you put openings in, this is a recurring theme. You will how should I say, any reinforcement that is interrupted by the opening shall be placed half on either side of the opening, okay, with proper development length. This is what we always do. It can be bent, very small openings. You can bend the reinforcement to go around the opening, but if it is an opening of any size, we will discontinue the reinforcement, but the discontinued portion shall be placed half and half on either side with proper development beyond the openings. Okay? So openings of any size shall be permitted in the area common to intersecting middle strips, provided total amount of reinforcement required. So intersecting middle strips, any area. In the area common to intersecting column strips, not more than 1/8 the width of column strip in either span shall be interrupted by openings. No more than 1/8 the width of the column strip. An amount of reinforcement equivalent to that interrupted, that part is the same always. In the area common to one column strip and one middle strip, not more than 1/4 of the reinforcement in either strip shall be interrupted by openings. Okay, so and all those requirements are summarized in this picture. So area common to two middle strips, you can put opening of any area at all. If it is in an intersecting middle strip, then there are severe limitations on the size of the opening. If it is in an intersection between a column strip and a middle strip, then there are restrictions on the essentially the size, although the language says not more than 1/4 of the reinforcement in either strip shall be interrupted by the openings. So anyway, the openings are provided for pretty explicitly. Okay, now we come to the the complication of flat plate design, I would say. Unbalanced moments. When gravity load, wind, earthquake, or other lateral forces cause transfer of moment between slab and column, a fraction of the unbalanced moment shall be transferred by flexure according to such and such. Now, let us look at what these unbalanced moments are. Okay. So, this is a slab strip, let us say, continuous over several columns. Under gravity, the top picture, this is what our bending moment diagram looks like. The blue lines indicate the bending moment diagram. Okay. At the exterior support, this entire moment, slab end moment, must be transferred to the column for equilibrium. That is the unbalanced moment transfer that we are talking about. At the first interior support, the bending moment to the left of the support is a bit larger than the bending moment to the right of the support. The difference between the two moments must be transferred from the slab to the column, and that is the moment transfer. By the time we have arrived at the second interior column, there is no moment to be transferred. The bending moment to the left of the column is the same as the bending moment to the right. So under gravity loads, there is significant moment transfer at the exterior support. There is some moment transfer at the first interior support, but then there is no moment transfer. However, if the same slab, or let us say the slab column frame, is called upon to resist wind loads or earthquake forces, the bending moments caused by wind loads will look like this. Now the green lines, the blue lines show you a very different kind of a bending moment diagram. That's how bending moments vary under lateral loads. This moment at the exterior support has to go to the column, no different from the case under gravity. But the big difference is at the interior column, every interior column, the unbalanced moment now is the sum of the bending moment to the left and the bending moment to the right. So unlike in the case of gravity, we now have significant transfer moment at every support, including every interior support. This is a huge difference between a slab that carries gravity only, a flat plate column frame that carries gravity only, and a flat plate column frame that also resists wind and earthquakes. Okay, huge difference when it comes to this unbalanced moment transfer. Now, when there is a moment to be transferred from the slab to the column at a slab column joint, part of it is assumed transferred by flexure and part of it is by shear. The part that is transferred by flexure is given by this expression, where B sub 1 and B sub 2 are the dimensions of the critical section for two-way shear. So gamma sub F is the factor used to determine, okay, gamma sub F is the fraction of unbalanced moment that is transferred by flexure. B sub 1 is dimension of the critical section measured in the direction of the span for which moments are determined. So B sub 1 is the dimension of the critical section for two-way shear in the direction of analysis. B sub 2 is the dimension perpendicular to the direction of analysis. And we will show you calculation of all of that. Okay, so now it is a different study. part of the same story, but a different aspect. So let us recap. The topic we are discussing is unbalanced moment transfer. I told you under gravity, it is pretty limited unbalanced moment transfer except at the exterior support. Under lateral load, that is not the case. There is significant unbalanced moment transfer at every support. When there is a moment to be transferred from the slab to the column at a slab column joint, part of it is transferred by flexure, that is gamma sub F times the unbalanced moment. The remainder is transferred by shear, that is 1 minus gamma times 1 minus gamma sub F times the unbalanced moment. Okay. Now, this is very, very I keep on saying is keep on using the word important. What I'm going to tell you next gives you a lot of flex. If you understand this, this gives you a lot of flexibility in flat plate design. Okay, and this was anyway. Let me not go there because it takes time. Okay, so for pre-stressed slabs with unbalanced moments transferred between slab and columns, it shall be permitted to increase the value of gamma sub F in accordance with the following. Okay, so gamma sub F by this expression comes to about 60% for, not about, it comes to 60% for square columns. If it is a rectangular column, you may calculate 62%, something like that. Okay, it's around 60% by flexure, 40% by shear. For non-pre-stressed slabs with unbalanced moment transferred between slab and columns, it shall be permitted to increase the value of gamma sub F from 0.6 in accordance with the following. For edge columns with unbalanced moments about an axis parallel to the edge, this is fancy language, but this is bending moment perpendicular to the edge. This is bending moment in the direction of analysis, the moment that interests us. Gamma sub F, which would normally be 0.6, can be taken as 1.0. Entire thing transferred by flexion, nothing by shear. Provided V sub U, the required strength at an edge support, does not exceed 75% of the shear that concrete alone can carry. V sub C is how much concrete can carry. Phi is 0.75, the strength reduction factor for shear. Okay, so gamma sub F, which would normally be about 0.6, can be taken equal to 1 all the way up to 1, provided V sub U at an edge support doesn't exceed 75% of what concrete can carry, and at a corner support doesn't exceed half of what concrete can carry. This is huge flexibility because the portion that is not carried by flexure is carried by shear. And that moment transfer shear adds to shear caused by gravity. And punching shear, I have been telling you, is the problem with flat plates. Okay, so this way we get to reduce. That's the way to look at it. It's not that we are increasing the portion of the unbalanced moment carried by flexure. We are decreasing the portion of the unbalanced moment that is carried by shear, thereby relieving the punching shear problem that we always have. So this is great flexibility if you understand how to use it. Okay. Now, that was bending moment perpendicular, bending moment at an edge column perpendicular to the edge. For unbalanced moment at interior supports and for edge columns with unbalanced moment about an axis perpendicular to edge, now the bending is parallel to the edge. So at an bending moment at an interior column or bending moment at an exterior column where bending is parallel to the edge, gamma sub f cannot be taken all the way to 1, but we can increase gamma sub f to as much as 1.25 times the value given by 13.13-1. So if we get 60.60 for gamma sub f, we can increase it to 0.75, okay? But something like that, 1/4 times the value calculated, we cannot go above 1.0. Now we can do that provided V sub u at the support does not exceed, here it is 40% phi times V sub c, quite restrictive. It was 75% at the edge column, 50% at the corner column. Now it is 40% of phi times V sub c at the interior support. In addition, the net tensile strain that I discussed with you, calculated for the effective slab width defined in, I don't think we have gone there, the effective slab width, it is coming up, shall not be less than 0.010. All of that will not register, but I will show you numbers. So the shear has to be low and the net tensile strain shall not be less than 0.010 for us to increase the gamma sub f at an interior support from 0.6 or something like that to 1.25 times that. Okay. The value of V sub c shall be calculated as prescribed in the code, and that we will also see coming up. Concentration of reinforcement over the column by closer spacing or additional reinforcement shall be used to resist moment on the effective slab width defined in such and such. Okay, let us go there. This effective slab width that they're talking about, and this concentration of reinforcement and so forth. Okay, this is this is something you absolutely got to understand. Okay, so this is obviously our column line. This is column strip, the shaded, and then there is a half middle strip, there is a half middle strip. Okay. The next column is here, and the next column to the front is here. This span is L2 sub A, that span is L2 sub B. The span in the direction of analysis, you know, is L sub 1. Okay. So the width of this column strip is L sub 1 divided by 4, or L sub 2b divided by 4, whichever is the smaller of the two. You know that, right? The width of this half column strip is L sub 1 by 4 or L sub 2a over 4, whichever is the smaller of the two. This b is a mistake. It should be a, and I couldn't correct it on the slide. Okay, so this is why I said note mistake on figure. This should be L sub 2a over 4. Okay, so we have our design strip from panel center line to panel center line. We have our column strip, and we have two half middle strips. Now, the column strip must have reinforcement to resist the column strip bending moment. The middle strips must have reinforcement to resist middle strip bending moments, goes without saying. But this moment transfer moment that we talked about, the unbalanced moment transfer, the portion of the unbalanced moment that is transferred by flexure, gamma sub f times m sub u. The portion of the unbalanced moment at a support section that is transferred by flexure, which is about 60% of the unbalanced moment, the reinforcement that you need to resist that moment must be placed within a narrow moment transfer band, I'm going to call it. It's not called that in 318. It must be placed within a narrow moment transfer band. This is what ACI is calling the effective width, the width of which is the column dimension in this direction, C sub 2, plus 1.5 times slab thickness on either side for a total of C sub 2 plus 3H. Okay, so the reinforcement required to resist the part of the unbalanced moment that is transferred by flexure must be placed within the moment transfer band, the width of which is C sub 2, the transverse column dimension, plus 1.5 times slab thickness on either side. Okay? This width of the moment transfer band is being called the effective slab width. So concentration of reinforcement over the column by closer spacing or additional reinforcement shall be used to resist moment on effective slab width. So to take the moment transfer moment within that narrow band may require closer spacing of slab up reinforcement or additional bars, as you will see when I show you an example. Okay, a slab, so now it is design method. A slab system shall be designed by any procedure satisfying conditions of equilibrium and geometric compatibility if shown that the design strength at every section is at least equal to the required strength. Okay? And that all serviceability conditions, including limits and deflections, are met. So any method that satisfies equilibrium and compatibility. Two such methods are specifically given in the code. The direct design method and the equivalent frame method. They have been in the code for a long time until they were removed from the code in ACI 31819. For quite a while, many 318 members have been saying this is textbook material, doesn't belong in the code and so forth, so it is gone. But you are on 31808, so you very much have both methods in your code, BNBC 2020. The direct design method is a hand computation method, gives you a feel for what you are doing. The equivalent lateral force procedure is done on the computer. You cannot do it by hand, I do not believe. So I have restricted myself here to the direct design method because I want you to share that feel for what we are doing. Okay? I had slides 30 some on equivalent lateral force procedure that I have removed from the slide set. We do not have time for that. Otherwise, I would have gone. And in any case, it does give you any feel. It is just prescriptions for the computer programs. Okay. Now this direct design method, which is what we will discuss for a while now, is applicable subject to certain limitations. Limitations are given in those sections 13611 through 13618. First limitation, there shall be a minimum of 3 continuous spans in each direction. And why that is necessary is in the commentary, which I will let you read. Panels shall be rectangular with a ratio of longer to shorter span, center to center of supports within a panel, not greater than 2. You know why not greater than 2. Okay? Panels shall be rectangular with a ratio of longer to shorter span, not greater than 2. Condition 3, successive span lengths center to center of supports in each direction shall not differ by more than 1/3 the longer span. Successive span lengths shall not differ by more than 1/3 the longer span. Again, the explanation is in the commentary. Offset of columns by a maximum of 10% of the span in the direction of offset from either axis between central lines of successive columns shall be permitted. So it's a regular column layout, but some offset of the columns is permitted. And I have a picture that will explain this language. That language is not particularly understandable upon reading. All loads shall be due to gravity only and uniformly distributed over an entire panel. The unfactored live load shall not exceed 2 times the unfactored dead load. This is a significant limitation, although in a concrete structure, this is not much of a limitation. Concrete is heavy. 6 inches of concrete is 150 pounds per square. Anyway, concrete is heavy. Typically, the live load on a concrete structure is a fraction of the dead load. So twice the dead load is quite a bit. So it is a limitation, but it is not an unreasonable limitation at all. And then this ratio for beam supported slabs only, for a panel with beams between supports on all sides, we have to satisfy this limitation. Alpha sub F1 is the beam to slab stiffness ratio that we have shown you. L sub 2 is the transverse span perpendicular to the direction of analysis. Alpha sub F2 is the slab to beam stiffness ratio in the transverse direction. L sub 1 is the span in the long direction. So this ratio has to be between 1/5 and 5. Alpha sub F is E sub the EI of the beam divided by EI of the slab. And the beam includes a part of the slab. All of that we have gone over. So this is kind of repeated. Alpha sub F was actually defined before, and we have said nothing new here. The elastic distribution of moments will deviate significantly from those assumed in the direct design method unless the requirements of stiffness are satisfied. So we are saying that particularly the last set of limitations is is quite important for accuracy of results. The usual moment distribution that we allow, remember 100 times epsilon sub t, that is not permitted with the direct design method, but we are allowed a 10% moment redistribution with the results of the direct design method. So the usual moment distribution doesn't apply because this is approximate or whatever, but up to 10% moment redistribution is specifically permitted by section 13617. Same thing. So modification of negative and positive factor moments by 10% shall be permitted, provided the total, you cannot violate statics. Now, variations from the limitation shall be permitted, demonstrated by analysis. Those things, I don't know how important. This also I will let you read. Okay, so the limitations under which you are allowed to use the direct design method. Most of it, I think, was understood upon reading. It is this offset that may not have been. So this is the maximum offset that is permitted. Okay, L sub 2 is this is the direction of analysis from left to right. L sub 2 is the perpendicular span, and maximum offset of this column would be L sub 2 over 10. Okay, everything else we have gone over and is repeated in the picture. Okay, what is the direct design method? It's a three-step affair if you want to look at it that way. We calculate the static moment WL squared by 8 moment for every span. We distribute the moment, the total static moment, between the two support sections and the span section. Okay, the support section moments are negative moments, the span moment is positive moment. And then each of those, the support section moment, the negative moment at the support, acts over the entire panel width. We assign some of that to the column strip and the remainder of that to the middle strip. Similarly, the positive moment in the span also applies to, it is for the entire panel width. Part of it is assigned to the column strip and part of it to the middle strip. So calculate free span moment for each span, distribute that between negative moments at the two support and the positive moment in the span, and then each negative moment and positive moment is distributed between column strip and middle strip. So this is our subsystem for slab design. Okay, we have our design strip and the columns attached are assumed fixed at their remote ends. Okay, when we talk about free span moment, this is the moment WL squared by 8 moment. It is Q L sub 2 L sub n squared by 8. Q is the it says someplace Q sub U is the load on the slab in I was going to say pounds per square foot. It would be whatever in metric units. Okay, so load on the slab, you multiply that by L sub 2, you get slab load in pounds per linear foot in our units. Okay, and then so pounds per linear foot and then L sub n squared, the clear span in the direction of analysis squared by 8. Q is in pounds per square foot in American units, the slab load. We multiply that by L sub 2, we get load in pounds per linear foot of the span. That multiplied by the clear span squared divided by 8 is the free span moment M sub 0, static moment. Okay, so M sub 0. M sub 0 is m sub 1 plus m sub 3 divided by 2, the average of the two support moments, plus the span moment, m sub 2. Okay, so m sub 2 has to be divided among those three, m sub 1, m sub 2, m sub 3. These details, I don't know, I was hesitating whether to read or not, where the transfer span of panels on either side of the central line of supports varies, L sub 2 shall be taken as the average of adjacent transfer spans. Okay, I think that is understandable upon reading. When the span adjacent and parallel to an edge is being considered, the distance from edge of panel central line, the distance from edge to panel central line shall be substituted for L sub 2. Okay, so if you don't have a panel central line on the other side but an edge, you will go from panel central line to the edge. Okay, so this is this is pretty much the story. This is a plan. So at the edge, this is what we are designing, and this is a strip centered on an interior. So this is a strip centered on an interior column line. This is a strip centered on an exterior column line, although centered on may not be the right language. So we will design this strip, that strip, that strip, that strip, and then when all the strips are done, we have the slab design. Okay. This is what we were talking about, the average. Okay, the L sub 2 would be the average of L sub A plus L sub B. And anyway, so the picture is pretty explicit. I don't know that I can add anything to that. Now, clear span L sub N shall extend from face to face of columns, capitals, brackets, or walls. Value of L sub N shall not be less than 65% of L sub 1. This is quite important. Okay. Circular or rectangular polygon shaped supports shall be treated as square supports with the same area. So span cannot be, clear span cannot be taken as less than 65% of the center to center span. Also circular or rectangular regular polygon shaped supports shall be treated as square supports with the same area. So this is what is shown here. Circular, you can replace by the square support. Okay. Now this may be helpful. So support face will be the face of this square. Support face here will be the face of this. Support face here is unchanged. Now this is a very long column. Remember the clear span cannot be any less than 30. The clear span cannot be any less than 65% of the center to center span. So 35%, half of that is 17.5%. So essentially the support face moves here. 17.5% of L sub 1 from the support central line, so that the span itself will be 65% of the clear span. Okay, so and when there is a hunch, you go from the total hunch has a length L. The face of support will be taken from A over 2. So this picture, I think, tells you the whole story. I don't know that you will have to deal with any other situation. So total factor moment M sub 0, part of it is positive bending moment, part of it is negative bending moment, and we will distribute the positive bending moment to column strip and middle strip, and the negative bending moment also to column strip and middle strip. Okay, I kind of forgot about the break. Let us take a 5 minute break, come back at a quarter to the hour. We are probably running late, but I don't know. Whatever. Yeah. So 5 minutes, quarter to the hour, we will start again. Okay, 5 minutes are up, so let's start again. Uh, we are talking about distribution of m sub 0 to negative and positive moment sections. So negative factored moments shall be located at faces of rectangular supports. If it is other shaped support, then you will come up with an equivalent rectangle as shown previously. Now, in an interior span, very important, interior span as opposed to exterior span, total static moment shall be distributed 65% to the supports, 35% to the span. Very simple. Okay? So 65, 35, 65 to the support, 35 to the span, if it is an interior span. If it is in an end span, total factor static moment m sub 0 shall be distributed as follows. Now it is not that simple, obviously. Let us take a particular case, then it will give you a good feel. So I am emphasizing, you must have noticed throughout the presentation, the flat plate, the slab supported directly on columns, no local thickening like drop panels, and no edge beams. Okay, this is our column. Slab without beams between interior supports, without edge beams. Okay, if that is our case, the interior negative factored moment, the factored moment at the end. So this is an end span. The negative factored moment at the interior support is 70% of m sub 0. The span moment is 52% of m sub 0. And the negative moment at the exterior support is 26% of m sub 0. 70 plus 26 is 96. Half of that is 48. So average negative moment is 48% plus 52% gives you 100% of m sub 0. Okay, so 70% of m sub 0 at the first interior support, 52% in the span, 26% of m sub 0 at the exterior support section. This is for the end span of a flat plate. The interior span, it is 65, 25, 65, not 25, 65, 35, that's 100. 65, 35 distribution, okay? 65% to the support, 35% to the span. Negative moment section shall be designed to resist. So here you have 70% of m sub 0 on the left side of the support, 65% of m sub 0 at the right side of the support. Negative moment section shall be designed to resist the larger of the two interior negative factored moments determined for spans framing into a common support unless an analysis is made, etc. Okay, so larger. Okay. Edge beams or edges of slab shall be proportional to resist in torsion their share of the exterior negative factor moment. So if the exterior support is a beam running in the transverse direction, so the slab end moment that we are talking about, 26% of m sub 0, that will be, if there is an edge beam, that will cause torsion on the edge beam. Okay, and that's what we are talking about. Edge beams or edges of slab shall be proportional to resist in torsion their share of exterior negative factor moment. Okay. The gravity load moment to be transferred between slab and edge column in accordance with it shall be. This is a this doesn't read like much. This is something I would say quite important. You absolutely cannot overlook it. 13636. Okay, what this is saying is something almost a little bit strange. So the moment here is 26% of m sub 0, the negative moment in the slab at the exterior support. So normally you will expect to transfer the 26% of m sub 0 to the column. But ACI 318 is specifically telling you instead of transferring 26% of m sub 0, when you are doing shear design only, not flexural design, you will transfer 30% of m sub 0. You will increase the transfer moment because that is conservative with respect to shear. Okay, remember, part of the unbalanced moment is transferred by eccentricity of shear, and that adds to punching shear stresses caused by gravity. So if we want to be in an attempt to be conservative with respect to punching shear, we are arbitrarily increasing the 26% of m sub 0 to 30% of m sub 0 to be transferred from the slab to the column for the purpose of shear design only. Flexural design will continue to be based on 26% of m sub 0. So please note this section to be, it is easily overlooked, but it is very important. Okay. Now, we have m sub 0. We have distributed that to support moments and the span moment. Now, this support moment is for the entire width of the panel. And across the width of the panel, this support moment does not vary uniformly. The variation is more like shown in the picture. Similarly, this positive moment is for the entire panel width. But across the panel width, the positive moment is not uniform. It varies as shown in the picture. So instead of taking this complicated variation for design, we go for a simplified variation like this, the stepwise variation. For the support section as well as the span section, we take a stepwise variation. In reality, we assign 75% of the negative moment to the half column strips and 25% to the middle strip. Okay, 75-25 distribution. And when it comes to the span section, we assign 60% of the positive moment to the two half column strips and 40% of the positive moment to the middle strip. So that is the distribution in the transverse direction. So at the support section, it is 75-25 distribution between column strip and middle strip. In the span section, it is 60-40 distribution between column strip and middle strip. Okay. So interior negative factored moment. Interior negative factored moment. How much of that goes to the column strip is what this table is telling us. Interior negative factored moment. How much of it, the total interior negative factor moment over the entire panel width, how much of it goes to the column strip. Okay. Depends on L sub 2 over L sub 1 and whether we have column line beams or we don't. Our line is here, no column line beams, flat plate. So it is 75% of the interior negative factor moment going to the column strip, as I mentioned already. That's what this section gives you and this table. Okay. So for no column line beam, 75% of the interior negative factor moment goes to the column strip, irrespective of L sub 2 over L sub 1 ratio. This is now exterior negative factor moment. How much of it goes to the column strip? Okay. If there is no column line beam and there is no edge beam, 100% of the negative moment goes to the column strip, 0% to the middle strip. Okay, this is very important, obviously. So exterior negative factor moment, exterior negative factor moment. If there is no column line beam, alpha sub f1 is 0, and beta sub t, which I have not explained yet, I will. If beta sub t equal to 0, that means there is no torsional member, there is no edge beam. Then 100% of the exterior negative factor moment goes to the column strip. Okay, this beta is given by this expression. C is a torsional coefficient, whatever it is called. C is given by this expression. So constant C for T or L beams shall be permitted to be evaluated. So to calculate C, you will take your section. This is your beam section. Remember, part of the slab becomes part of the beam. You will divide the beam section up. You can do it only two different ways. This rectangle goes up to here and then that rectangle, or this rectangle comes all the way and this rectangle. Whichever way, you can divide it both ways. Whichever way you get the larger C is, that's what you use. So constant C for T or L sections shall be permitted to be evaluated by dividing the section into separate rectangular parts and summing the values of C for each part. And you are allowed to take the largest of the values that you get by dividing the section differently. So C is the torsional constant. C this is I slab. Anyway, so this is the beta sub t that we are talking about in the previous picture. Now, the effect of the torsional stiffness parameter beta sub t is to assign all of the exterior negative factor moment to the column strip and none to the middle strip, unless the beam torsional stiffness is high relative to the flexural stiffness of the supported slab. Okay. So 100%, 0% distribution when there is no edge beam or the edge beam doesn't have much of a torsional stiffness. Some of these details, maybe it will be better if you just read. I think, I don't know that I have anything to add. Yeah, this is not unimportant stuff if you have walls, but I think Just a reading will tell you what it is about. Where supports consist of columns or walls extending for a distance equal to or greater than 75% of L sub 2. Negative moment shall be considered to be uniformly distributed across L sub 2. Again, pretty easily understood. And those are kind of details that have evolved over the years. So we talked about distribution of negative moment, interior negative moment, exterior negative moment. Now it is positive factor moment. How much goes to the middle strip, how much to the column strip. So this is our situation. No column line beam or column line beam isn't stiff enough. It is 60-40 distribution, as I mentioned earlier. 60% going to the column strip, 40% to the middle strip. So for slabs with beams between supports, the slab portion, so if there are beams between supports, the slab portion of column strip shall be proportion to resist that portion of column strip moment not resisted by beams. Okay, if the column strip includes a column line beam, then part of the moment will be resisted by the two strips of slab on the two sides of the column and the remainder by the beam. Okay, that's all we are saying. When slabs have beams between supports, moment distribution depends on the beam to slab stiffness ratio alpha sub F1, the beam to slab, yeah, anyway, so all of that, this is a repeat again, beam to slab stiffness ratio, and these charts were devised to make it easier to calculate the beam to slab stiffness ratio. Okay, if the column line, if the column strip does include a beam, beams between supports shall be proportional to resist 85% of the column strip moment. If the beam is reasonably stiff, okay? So the beam takes 85% of the column strip moment and the strips of slab on two sides of the beam carry only 15%. This is for values of alpha sub F1, L sub 2, or L sub 1 greater than 1. If the value is less than 1, then you interpolate down to so proportion of column strip moments resisted by beams shall be obtained by linear proportion between 85% and 0%. Okay? I think this is very easily understood if you just read. In addition to the uniformly distributed loads we are dealing with, beams shall be proportional to resist all moments caused by concentrated or linear loads applied directly to beams, including weight of projecting beam stem above and below the slab. So anything that doesn't go to the column strip goes to the middle strip. So each middle strip shall be proportional to resist sum of moments assigned to two half middle strips. That is pretty much common sense. A middle strip adjacent to and parallel with a well-supported edge shall be proportional to resist twice the moment assigned to the half middle strip corresponding to the first row of interior supports. This again, if you look at a picture and read, you will see what is being said. Okay, so that is pretty much the story of the direct design method. Equivalent frame method, I said we will not discuss. So let us spend, I think I have 25 minutes before regulation time. Let us look, let us spend real good quality attention on this example, which I think will drive things home. Okay. So this is a slab column structure, 5.5 meter span in one direction, 4.3 meter span in the orthogonal direction. We will design the blue slab strip in running in the up and down direction, which is the direction of analysis. Okay. So the strip that is in blue is what we will design, centered on an interior column line. Structural system, two-way slab without beams, no edge beams. We will do the direct design method. Concrete strength 40 MPa. The weight of the concrete 2400 kilogram per cubic meter. That tells you it is normal weight concrete. Reinforcement 420 megapascal yield strength. 400 by 400 millimeter columns. Live load 2 kilonewton per square meters. Partition load is 1 kilonewton per square meters. Partition load is non-reducible. Okay, you have to know that. The minimum thickness required, I will not go all the way back. You can look at table 9.5C, the right row. The minimum slab thickness required by that table 9.5C is clear span divided by 30. We have a clear span of 5,500 center to center span minus column dimension of 400 divided by 30. That gives us 170 millimeters. That is minimum thickness. We are going to provide 200 millimeters, nice and round. Absolute minimum thickness is 125 millimeters. Obviously, that is not a problem for us. Dead load, 200 millimeters is the slab thickness. 2,400 kilograms per meter cubed is the unit weight of the concrete. 9.81 meter per second is the value of G. So all of that together gives you 4.7 kilonewton per square meter of dead load. Live load is given, I think it was 2 kilonewton per square meters. Yeah. Like that 2 kilonewton per square meters is reducible. We can take live load reduction as given by this expression, and this is in the IBC. I should have given you the BNBC section number. Anyway, we get 8.4% live load reduction for our tributary area, which is 5.5 times 4.3. That is the 23 points. Here is the calculation. 4.3 times 5.5 is 23.65 square meters. So 8.4% reduction. That brings the 2 kilonewton per square meter down to 1.83 kilonewton per square meter, 8.4% reduction. Okay. Partition load 1 kilonewton per square meter, unreducible, non-reducible. So total live load is the reduced 1.83 plus the unreduced 1.0 for a total of 2.83 kilonewton per square meters. Under gravity alone, we have two load combinations to consider. 1.4 dead load, that gives you so much, or 1.2 dead load plus 1.6 live load, that gives us 10.2 kilonewton per square meter. That obviously governs way more than 6.58. So that's our load, 10.2 kilonewton per square meters. Okay. First, we check for shear, which we haven't discussed yet. That is our topic tomorrow. Should I even, maybe I didn't think of it beforehand, but maybe I will just skip this. You will say the same things tomorrow. We will do the same example because shear we really have not covered, and that will save us time. We can spend more time on things that we need to discuss. Okay, so the shear design I'm skipping today, but we will do all of that tomorrow. Okay, now direct design method. Remember, we have to meet a number of conditions. We have to have at least 3 continuous spans in each direction. We have 3. The aspect ratio cannot be any more than 2. Our aspect ratio is 5.5 divided by 4.3. Long direction, we have 5.5 meters. Short direction, 4.3. That is 1.28, obviously less than 2. That is satisfactory. Successive span lengths cannot be different by more than a third of the span. We have equal spans, so that condition is met. Columns can be offset by a maximum of so much, but we don't have any offset columns, so that condition is met. Live load to dead load ratio cannot be any more than 2. Our live to dead load ratio is 0.6. So this is pretty typical of concrete, what you are looking at. Okay, we would, unless it is a warehouse or something like that, we will not approach that number of 2. And the final was the stiffness ratio. Remember, alpha sub m1 L2 squared divided by alpha sub f2 L sub 1 squared had to be between 0.2, a fifth, and 5. But we don't have any column line beams, so that 6th condition simply does not apply to us. So we have satisfied all the conditions that apply. That means direct design method can be used in our particular case. Okay. So first step, calculate free span moment. Q is 10.2 kilonewton per square meter. L sub 2, the transverse span 4.3 meter. Clear span is 5.5 minus 0.4, which is 5.1 meter squared divided by 8 as 142.6 kilonewton meters. Okay. So 142.6 kilonewton meters. Interior span, the distribution is 65% to the supports and 35% to the span. For the end span, the distribution is 70% of M sub 0 is the interior negative moment, 52% is the span moment, 26% is the exterior negative moment. Okay. So we are now talking about the interior span. So positive moment is 35% of M sub 0. Interior span, positive moment is 35% of M sub 0. 60% of that is the column strip moment. 40% is the middle strip moment. The 60% of 35% of M sub 0 comes to 30 kilonewton meters, and 40% of 35% of M sub 0 comes to 20 kilonewton meters, because we know the value of M sub 0. So for the interior span, the column strip positive moment we have found, the middle strip positive moment we have also found. Okay. The negative moment is 65% of M sub 0. 75% of that goes to the column strip, 25% of that goes to the middle strip. The column strip negative moment comes out to 69.9 kilonewton meters. The 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 negative moment in the middle strip comes to 22.8 kilonewton meters. Okay, so interior span, positive moment 30 kilonewton meters in the column strip, 20 kilonewton meters in the middle strip. Negative moment, both supports are the same. This is interior span. 69.9 kilonewton meters is the column strip moment, 22.8 kilonewton meters is the middle strip moment. Okay, then the end span. We now have interior negative, positive, and on the next page will be exterior negative. We now have 3 sections to consider, not just 2. Interior negative moment is 70% of m sub 0. 75% goes to the column strip, 25% to the middle strip. The column strip moment comes to 75.6, the middle strip moment to 24.2. This is interior negative moment, column strip so much, middle strip so much. The positive moment in the end span, column strip 60% comes to 44.2 kilonewton meters, middle strip 40% comes to 30 kilonewton meters. Okay, so end span, interior negative moment, so much to the column strip, so much to the middle strip. Positive moment, so much to the column strip, so much to the middle strip. Now the exterior negative moment, this is exterior negative moment, remember, is 26% of m sub 0. This is a situation where, as we discussed, it's 100%, 0% distribution, 100% going to the column strip, 0% to the middle strip. So exterior negative moment, the column strip gets all of the 26% of m sub 0, which is 37.1 kilonewton meters, and the middle strip gets 0. Okay, so anyway, this table you have seen. Okay, what is our column strip width? We have 2 spans, 4300 and 5500. Shorter obviously is 4300. So column strip width is half of that, 2150, and the middle strip that is left over then is also 2150. I hope this is not a problem. It's totally unnecessary to go back. There are only 2 spans in the picture, 4300, 5500. 4300 is obviously the shorter. So remember, a column strip is made up 2 half column strips, and each half column strip is 1/4 of the shorter span. So the column strip width is half the shorter span, which is 2150, and that will leave middle strip width to be the remaining 2150. Now the minimum reinforcement, flexural reinforcement, and the maximum spacing. Minimum flexural reinforcement is the same as the shrinkage reinforcement for grade 480. It is 0.18% of gross. So 0.18% of the gross section, 2150 is the width, 200 is the total thickness, that is 774 square millimeters. And maximum spacing is twice the total thickness of the slab, that is 400 millimeters. These are both very important numbers. So Flexural reinforcement cannot be any less than 0.18% of the gross section, which is 774 square millimeters. Maximum spacing cannot exceed twice the thickness of the slab, which is 400 millimeters. So if we use 7 number 12 bars, A sub S would be 791 square millimeters, and that is barely above the 774. So we cannot ever provide in this slab less than 7 number 12 in either the column strip or the middle strip. Okay, both have a width of 31, what was it, 2150. Okay, this 2150 millimeters. Okay, now we are at the end support. The M sub U is 37.1 kilonewton meters. That was, once I start doing that, it's a, but that was determined a long time ago. Uh, the, I don't see the number, doesn't, okay. Uh, okay, let us not look, it must have been there, I cannot, I don't want to spend any more time looking for it. So the bending moment at the exterior support, end support, 37.1 kilonewton. Maybe we just got it here. Yeah, this is it, 37.1. Okay. This is the end support moment, 100% going to the column strip, 0% going to the middle strip. So this 37.1 kilonewton meters of bending moment at the exterior support. All of this is unbalanced moment, obviously. Okay. For this bending moment, the required A sub S for our slab thickness is 583 square millimeters. That being less than the 0.18%, we have to provide the minimum. That is 7 number 12. Additional flexural reinforcement required for moment transfer is computed. The total unbalanced moment. So the bending moment itself requires 7 number 12. Okay. Now the unbalanced moment is 37.1 kilonewton meters. The whole thing has to go from the slab to the column. How much of it is transferred by flexure? How much by shear? We calculate that 62% goes by flexure. This B sub 1 is 400 plus. So this is an exterior support section. This critical section for shear again is something that has not been discussed. It is tomorrow's topic. But anyway, this is an exterior column. So one dimension is the column dimension plus 1/2 of D, effective depth of the slab. The other dimension is the column dimension plus the full effective depth of the slab. So 570 and 485, that gives us the 0.62. So for now, the 0.62 is partly based on trust that those are the values of B sub 1 and B sub 2. Now, I want to emphasize that you absolutely must pay special attention. Okay. So we have an unbalanced moment of 37.1, I think it was 37.5, 37.1 kilonewton meters. Okay. And our calculation says 62% of that is transferred by Flexure. Remember, I mentioned that flexibility that ACI 318 provides. My friend Jacob Grossman spent back in the early to mid 80s, you would not believe how much effort to get this into ACI 318. We can increase the 62% to 100% entire unbalanced moment taken by Flexure if, remember, V sub u at an edge column is less than 75% of what concrete can carry, phi times V sub c. Okay. First, I'm saying if we do not want to take advantage of that flexibility, if no advantage is taken of that ACI section, then unbalanced moment transferred by Flexure would be 62% of the 37.1 kilonewton meters of unbalanced moment. That will give us 23 kilonewton meters. Required area of reinforcement to resist that moment in the 1000 millimeter wide strip. That calculation I did not show you. I probably should have written that. The 1000, remember, is the column dimension, 400, plus 1.5 times the slab thickness on either side. So 400 times the slab thickness is 200, 1.5 times that is 300. So 400 plus 300 on one side and 300 on the other side gives you 1000 millimeters. 1 meter is the width of the moment transfer band. Okay. So the required area of reinforcement to resist this moment in the 1000 millimeter wide strip is 363 square millimeter. You can calculate that pretty easily. Okay, so this is our transfer moment. If we want to stick to 62% going by Flexure, and that moment requires 363 square millimeters of reinforcement in the moment transfer band. So 363. 3 number 12 was short, so we had to provide 4 number 12. That comes up to 452 square millimeters within the 1000 millimeter width over the column. So spacing of those 4 bars is 333 millimeters, which being less than 2 times H or 400 millimeters, we are okay. So we will provide 4 number 12 inside the moment transfer band, which has a width of 1000 millimeters. Our column strip width is 2150. So outside of the 1000 millimeter moment transfer band, we will provide 4 number 12 bars. The spacing of those bars is still less than 400 millimeters, so we are fine. So we are providing 8 number 12 bars in our column strip. And this is the picture. Within the moment transfer band, which has a width of 1000 millimeters, we are providing 4 bars. And outside of the moment transfer band within the column strip, we are providing 2 bars or no, 2 bars to the left, this one and that one, and 2 bars to the right for a total of 8 bars. Total area 904 square millimeters. Okay. So that's when we did not take advantage of the flexibility that we have. We transferred 62% of the unbalanced moment by Flexure. Now we want to take advantage of what Jacob Grossman gave us. So for moment at an edge column perpendicular to the edge, the value of gamma sub f may be increased to 100% provided the V sub u is less than 75% of phi times V sub c. In this example, V sub u is 127 kilonewtons and 75% of V sub c is 307.5. Now, you have not seen that. This is tomorrow's topic. I'm not sure I showed you V sub u. Uh, anyway, you can definitely trust me on that. we have the condition satisfied that will give us gamma sub f of 1, V sub u less than 75% of phi times V sub c. Unbalanced moment transferred by Flexure then is 100% of the 37.1, which is 37.1 kilonewton meters. The required area of reinforcement to resist this moment in the 1000 millimeter wide strip is 605 millimeters. That would, so 5 number 12 bars didn't do. We had to provide 6 number 12 bars. That was total area of 678 square millimeter within the 1000 millimeter width. Spacing of that is 200 millimeters, which is less than maximum. Outside of the 1000 millimeter width, we provided 4 number 12 bars and the spacing was fine. So now we are looking at a total of 10 bars, 6 within the columns, 6 within the moment transfer band, and 4 outside because we are transferring a lot more moment, 100% rather than 63% of the unbalanced moment. Okay, so this is what the column strip looks like: 6 bars in the moment transfer band and 4 bands, 2 on this side, 2 on the other side, 4 bars outside for a total of 10. So when you transfer more moment, this is what you get. You will have more bars within the moment transfer band and consequently more bars in the column strip. This looks like a penalty, and I keep on using the language, take advantage of this. It looks like penalty here, but if you look at the shear part, now you are transferring no unbalanced moment by shear. Okay, so you don't have any additional punching shear stresses caused by moment transfer. You are so much better off. That is the big price that we are after. So we are relieving shear at the cost of adding some flexural reinforcement. And this is an easy bargain. This is highly desirable most of the time. You will see the shear side of the story tomorrow. I will show you the same example and do the shear part. Okay, so we go from the exterior support section now to the interior support. The bending moment at the interior support, on one side it is 70% of m sub 0, on the other side it is 65% of m sub 0. 70% of m sub 0 comes to 75.6 kilonewton meters, 65% comes to 69.9 kilonewton meters. It's the small difference between the two that is the unbalanced moment. So typically we don't have, under gravity, a lot of moment to be transferred at the unbalanced moment. Anyway, so the 75.6 kilonewton meters requires 1201 square millimeter of reinforcement. That is more than minimum. That requires 11 number 12 bars. Okay. And the 69.9 kilonewton meters of negative moment requires 1109 square millimeters, but we will provide the same 11 number 12. we provide the larger amount. The unbalanced moment, as I said, is the difference between the 75.6 and the 69.9 is a very small 5.7 kilonewton meters. 60% will go by flexure because this is a square column interior section, and 40% by shear. Okay? Okay, now for this 5.7 kilonewton meters of unbalanced moment, nobody in his right mind would do this, but I wanted to show you this flexibility. When you are doing earthquake design or wind design, you will have huge unbalanced moment at an interior support, and then this comes in very handy. Okay, so for interior column, the value of gamma sub f may be increased by 25%. The 60% can be increased to 75%, provided the V sub u is less than 40% of phi times V sub c. This is very restrictive, and there is an additional requirement that I will show you. In this example, V sub u is 238, 40% V sub c is 243. So we barely met it, barely, but we did. If the 11 bars in the column strip are provided at a so the other condition that has to be met is what I'm illustrating here now. Okay. So we said 11 number 12 bars in the entire column strip. If the 11 bars in the column strip are provided at a uniform spacing, the spacing then will come to 215 millimeters, 10 spacings, and 2150 is the total width. There will be 5 number 12 bars in the effective width equal to 1000 millimeters. You see what I'm saying? We have 11 bars in the column strip. If they're uniformly spaced, the spacing will be 215 millimeters. That will indicate that we have 5 bars within the moment transfer band, which has a width of 1000 millimeters. Okay. Now, in that 1000 millimeter width, 200 millimeter deep slab having an effective width of 170 millimeters. If so, we know our section 1000 wide. It has a depth of 200 millimeters. Effective depth, if you calculate for the number 12 bar, comes to about 170. So for the moment that has to be carried, the stress block depth comes out to 7 millimeters. Okay, 7 millimeters. For the moment that this moment transfer band will resist, gives us 7 millimeters of stress block depth. For 40 MPa concrete, beta sub 1 is 0.76. So the neutral axis depth is 9.08 millimeter. So the net tensile strain by straight line strain distribution comes to 0.53. And for us to increase gamma sub f to 1.25 times gamma sub f, this net tensile strain has to be larger than 0.01. We made it like without any problems. Okay, so the 60% of gamma sub f equal to 0.6 can be increased to gamma sub f of 0.75. and that will decrease the shear portion to 0.5 from 0.35. Okay, so that is the limited flexibility that is allowed at an interior joint, very much less than what we have at the exterior support. But this again can be meaningful when we are doing wind or seismic design, because we have huge unbalanced moments at the interior support sections. So unbalanced moment transferred by flexure is 4.3 kilonewton meters. The required area of reinforcement to resist this moment in 100 millimeter wide strip is 67 millimeters, which is less than one number 12 bar. So the 11 number 12 bars provided in the entire strip is sufficient. So in other words, the unbalanced moment at the interior support section is so insignificant that we do not have to add any bars in the column strip. So the 11 number 12 that we start with, uniformly distributed, that is good enough. Okay, so this is what we have provided at our interior support section. 11 number 12 at a uniform spacing of 215 millimeters. This is good enough for the transfer moment as well. And this is a summary of everything that we have done with this. Some of it didn't have to be shown because it is minimum moment. Anyway, this is a summary of the entire design of that strip that we set out to design. This 8 or 10, depending upon, if you want to transfer 100% of the moment, it becomes 10. If you transfer only 62% of the unbalanced moment by flexure, then it is 8. So that is the difference. We had a choice there, and we did it both ways. Okay, I'm late by quite a bit, but again, now I'm open for questions, and we will do it the usual way. Bodhi will read me questions, and I'll try to answer. Thank you very much.
Thank you, Dr. Ghosh.
Thanks.
So I would start with questions. Few of them I've already answered. So
okay.
So many of them asked, like, for analysis last week when you showed the stiffness modifiers for cracked sections. So for 0.25 is specified for flat slabs. So if there is a beam supported slab, then what should be the stiffness modifier?
In analysis, I don't know, beam supported slab, we have stiffness for beams.
Yeah.
So I do not know that beam supported slab we require a separate stiffness modifier.
Okay. Yeah. I think that will answer 3 or 4 more questions.
In the analysis, it doesn't. I mean, the slab is not taken as part of the beam and things like that. We go with the beam stiffness.
Okay. So for the flat plate slab system, what kind of framing system will it be called in seismic force resisting system if there is no shear wall?
This is a a very important question, and it will come up in the seismic sessions. Okay, I will give you a fairly brief answer. In flat plate column frames can be part of the seismic force resisting system of a structure only up to design category C. Beyond design category C, in design category D, E, or F, E or F you don't have Bangladesh, so don't worry about it. In design category D, A flat plate column frame cannot be part of the seismic force resisting system. So in design category D, what we do is to take the seismic forces on shear walls or braced frames, and then we design the flat plate column frames to carry gravity only. And then the combination is designed as a we have choices. We can do typically it will be a building frame system, as it is called. The shear was carrying 100% of the lateral loads, the frames carrying all the gravity, and we have to satisfy deformation compatibility between the frames and the shear walls. The frames must continue to carry 100% of the full factored gravity loads as they deform together with the seismic force resisting shear walls all the way up to the design earthquake displacements. So in summary, flat plate column frames by themselves cannot be part of the cannot be the seismic force resisting system of a building assigned to design category D.
Thank you, Dr. Ghosh. So can we place flexural reinforcement outside the web of a beam at flanges within the 4 into slab depth area?
Is that a question?
That's a question.
Read that again.
So can we place flexural reinforcement outside the web of beam at the flanges? And he's talking about the effective width. Within the effective width, can you place flexural
This
reinforcement?
question was asked the other day, and the
Yeah,
answer is
last
yes.
week.
Yeah, the answer doesn't change from day to day. Yeah, if you have a T-beam, this has nothing to do with today's discussion. If you have a T-beam of any kind, part of the slab acts as the beam, the effective beam width will go to what is in, I forget, section 812 or something of the code. And yes, the flexural reinforcement can be placed, some of it can be placed within the effective slab width.
Okay. So there is a suggestion to include expansion joints also in our lectures. I don't know if we are including in any of the lectures.
Say that again.
So there's a suggestion to include expansion joints of buildings in our lectures.
I don't know what that means.
Just some context about expansion joints and stuff. That is if that can be discussed in one of our webinars. That's just a suggestion. It's not a question.
Okay.
Yeah.
We talked quite a bit about expansion joints, that they're a nuisance and should be avoided. So
Yeah.
that's what I would like to iterate.
Okay. And we consider the shear resistant capacity of column strip rebar during the punching calculation of flat plate.
No, I didn't understand. Read it again.
And we consider the shear resistance capacity of column strip rebar during the punching calculation of flat plate.
During punching calculation, he wants to consider the shear resistance of the column strip reinforcement.
Yeah.
I see. Second. That is currently not included in the punching shear stress. It's currently not included. This will be our topic tomorrow. So maybe we'll see the answer from the presentation, but it is not considered, would be my opinion, my answer. Yeah, I'm not saying that it may not contribute. I don't know, but it is not considered.
Okay, Dr. Ghosh.
Mm.
So moving on. So there is one question.
Mm.
So Dr. Rakib is also there as a co-host. So if
Mm.
it's related to BNBC, if needed, he can pitch in.
Mm.
So in BNBC, alpha F1
Mm.
I2 by I1 uh,
Mm.
is written greater than or equal to 1, but you showed greater than 0, which is correct.
We have to go to the specific place. I don't know. I mean, this is not an absolute question. You have to
Yeah,
point out where.
they're same, right? Like I was thinking
Huh?
it's
Say that again.
the tables should be same basically in BNBC and ACI
Yeah,
table.
yeah. There is no difference. No,
Yeah, yeah.
no,
I think that's the answer. There's no difference. Like you can probably look at it once. Maybe there's
no.
some
There definitely is not that kind of a difference. No, absolutely not.
right.
So check whatever BNBC says, and if you can get hold of ACI 318 or you can send it to us, we'll check against ACI 318, and if the slide says anything different, we'll change it.
I think this question is regarding the example. Uh,
Hmm.
so it's very unclear without context, but I will just
Hmm.
uh, yeah, maybe you will understand. So
I
beam,
can. Yeah,
yeah,
go ahead.
beam resists 85% of M or 85% of 65% of M. So
Yeah, so what he's talking about is, yeah, so if the column strip includes a beam, please follow every word very closely. If our column strip includes a beam, then 85% of the column strip moment will be resisted by the beam, and the remaining 15% by the two strips of slab on two sides of the beam. Okay. Now, this column strip moment is a percentage of the slab moment, depending upon which slab section. The column strip moment may be 75% of the whole design strip moment. It can be 100% or I guess another number. So anyhow, when we are talking about 85% of the moment being carried by the beam, it is 85% of the column strip moment, not 85% of the design strip moment. I hope that that clarifies what you are asking.
moving on. So in our country, slab design practice, we currently practice crank slab rebar.
What river?
Crank slab rebar.
Crank slab.
Yeah,
CRANK?
yeah.
I don't know what that is.
When I don't know.
That is main reinforcement is bent from bottom to top.
Oh, in the slab.
No, in the beam it has been used, but this is very uncommon.
Yeah.
This is not used anymore.
No, slab is so thin that bend bars typically don't work. So I don't know what he's talking about. Yeah. So read the rest of it.
Is it right? I want to say, no, so he just wanted to know the disadvantages or advantages of that. So,
No, bend bars. Two things about it. Bend bars, at least in the U.S. and I would say most. I don't know. In most countries where labor is expensive, you cannot do bent bars because it is labor intensive. So it is gone. In the US, you won't see it, period. Where labor is cheap and it can be done, maybe it is continuing, I don't know. But bend bars would require a certain depth. I don't know that there is a code prescribed depth. I think in the case of slabs, there actually is. I forget now, 6 inches and 16 times the bar diameter, something like that. There is a provision uh, for, and maybe it will come up yesterday. You cannot use bend bars even if you want to, unless your slab thickness is beyond a certain minimum. And I cannot remember whether it is 6 inches or 8 inches. So, I find it difficult to believe what you are saying, that you have bend bars like common practice in Bangladesh. I doubt that. In beams it may be, in slabs I seriously doubt that. Okay.
okay, yeah. So is it possible to design flat plate or slab on steel columns? Are there any design considerations specific to that?
There is so-called, I didn't go there, what is it called? Lift slab construction, and that requires shear head. You 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 have to have steel shapes built into your slab that go around the steel column. All of this is provided for in SEI 318, and I suppose it is reproduced in BNBC. I do not know, but there are provisions. Yeah, look for lift slab construction and shear heads. Those are the key terms that you have to look for. And then you will see how that there are provisions allowing this to happen.
Could you please discuss about the technical issues of providing beam around large opening having depth equal to slab thickness? Equal to slab thickness. Can we analyze and design it like typical beams?
Can we analyze and design it like what?
Typical beams.
What beams?
Typical.
Oh, typical beams. Yeah. It's difficult to generally comment on. I mean, what you are suggesting can be done. There is absolutely no problem with it. I think in some ways this is an elegant thing to do, but then everything depends on the size of the opening, particularly relative to the panel in which you have the opening. And can you analyze it like conventional beams? I do not see why you will need to or want to. The main consideration will be the development of the bars beyond the opening. And if the thickness is the same, why would you want to analyze it? I don't know. I have to. No, it's difficult to comment on on a question like that. Yeah, no, I don't know, but what you are suggesting can be done. The analysis part is where I'm having trouble telling you anything of significance. but it's a good thought. What you are thinking of doing can be done, and there is absolutely, and in many cases it may be a pretty elegant and cost-effective solution because beams stick down and are very expensive to form. So if you can do whatever you need to do within the thickness of the slab, that's a good thing to do.
Thank you, doctors.
Mhm.
There are other questions which you have answered already.
Mhm.
I would suggest going through the presentation or the recording once afterwards,
Mhm.
because these are very simple questions.
Okay, so tomorrow we will do design for shear. I will skip more details than I did today to conserve time, and then hopefully we can fit in the two examples that are left over from development length, which keep on bothering me. And then we will answer a combined set of questions. I think that will, and if we go a little bit beyond 11, then so be it. Okay.
Okay, doctors. So I think, yeah, like we are already past 11 now. So
Yeah.
I will turn on the quiz, so you can go and attend the quiz. Also, as you know, that the feedback sections are new, something new that has been added to the training page. So you can provide your feedback for today's session in using that link. We would really appreciate your feedbacks regarding these training sessions. Thank you, Dr. Ghosh, for this wonderful lecture.
Thank you. Thank you.
See you tomorrow.
Yeah. See you.